Okay, getting into combinations now where order doesn't matter. If you're picking three students out of a class and they're going on a school trip, order doesn't matter here because if they call your name first or second or third, it makes no difference. You're still going on the trip. There's nothing special about being picked first or about being picked last. Now, how many ways can they do that? There's a few ways to set this up. And the one with filling in the blanks I actually have a little trouble with. It doesn't seem like the most straightforward thing to me. But what you end up doing is, if you have to pick three winners, and all 10 students are sitting there looking at you, then there's 10 choices you can put in this first space. And now there's only 9 students left that you could select for this second space, and there are 8 students left that you could select for this third space. And that comes out to 720, but that's not it. To finish this, we also have to say, well, hang on. These students could be selected in any order. So there are actually 3 times 2 times 1 internal arrangements of the winning students. Right? If you're selecting 3 students, then you could pick, there are 3 of them that you could have picked first, 2 of them that you could have picked second, and 1 of them that you could have picked third. Each of those is a different permutation, but it's the same winning group, no matter what order you picked them in. So to finish this, 3 times 2 times 1 is 6, we have to say, okay, there's 720 orders we could call the names, but only a sixth of them are actually different. Otherwise, you get things like Jeremy, Nancy, and Carly, you won, or Carmi, Jeremy, Nancy, you won. Mixing up the names doesn't change who won the trip. So dividing by 6 gets rid of all those extra arrangements and gets us down to 120. That's my least favorite way of setting this up. Here's one that I like better, and maybe you will too. Imagine that you were making up envelopes that you were going to hand out to see who's gets to go and who doesn't. So you have 3 winning envelopes, and then you have 7 losing envelopes that say, sorry, try again. And the students are sitting in front of you, and you're going to shuffle up these envelopes and then hand them out and let that be how they find out whether they're going or not. How many ways could you arrange these envelopes? Well, there are 10 of them, so we start with 10 factorial. The 3 winning envelopes are indistinguishable, and the 7 losing envelopes are also indistinguishable. If you work that out, there we are. If you use that to work out the number of combinations, you get 10 factorial divided by 7 factorial, and also divided by 3 factorial, which is just 6. And sure enough, you get 120. So 10 envelopes, you can't tell the 3 winners apart, you can't tell the 7 losers apart. And if you do this with a combination, you would say there are 10 students, I want to select 3 of them, and C means I don't care in what order they are selected, just whether they're selected or not. So if we try that, 10, probability menu, go to combination 3, 120. This method we'll probably never see again. I tried to set it up so that it would look similar to other things that you've done, but I found it awkward to do it this way and work out the number of duplications. This makes a lot more sense to me, and 10C3 is, of course, very simple, and we'll be working on it more in the coming examples.